Hello everybody. Today I'm going to present this paper FlexGPU, a flexible and efficient scheduler for GPU sharing system. This paper is accepted by CCGrid 2020. So currently, GPU is widely used in not only graphics processing fields but also in different fields such as HPC, AI, and cloud computing. And all of them needs large computation power. Meanwhile, the concept of GPU as a service are becoming the latest hardware trend. Currently, most of the cloud providers start to provide GPU as one of the service to satisfy customers' request of higher computational power. As a result, improving the efficient utilization of GPU resource becomes more important than ever. GPU multitasking is a good solution to improve the resource utilization because single workload usually may not use up all the resources. However, since GPU memory cannot be oversubscribed, it potentially decreases the possibility of running multiple applications on the GPU because exceed of the GPU physical capacity will cause an out-of-memory failure. Therefore, solving the GPU memory oversubscription issue can improve the utilization of GPU resources. Basically, GPU is designed to be monopolized used by a single application. In that case, since the program knows how much GPU memory they are going to use, they can cause the application to prevent exceed of GPU memory. However, in the multitasking case, because the workloads do not know how much memory the others needs, they may cause some problems. As shown in this figure, running workload 2 monopolizedly will cause no problem. However, execute it along with workload 1 will cause an LOM error. Since we already know that in HPC, AI, and applications running as cloud always within multiple kernels need to be executed, we observed some interesting facts in the multitasking environment. It seems to avoid the overhead of data movement from the host to device application, usually prefetch all the data to the GPU memory at first, and do not release them until the end of the program. So as shown in this picture, there are two kernels in the application, kernel 1 and kernel 2. Kernel 1 runs rarely but consumes much more GPU memory. And kernel 2 is on the opposite. It means it runs usually very often but consumes less GPU memory. So as a motivation, we are thinking about remove the will not be used data immediately to make space for other kernels and bring them back only if they are used again. There are already some research on this topic. In the case of dynamic GPU resource allocation, they dynamically allocate and release a GPU computational resource. However, GPU memory resource is not considered yet. They were implemented on the simulator, so it will be a little different with like implement on the real hardware. And in the case of client-server-based GPU resource scheduling, a scheduler process manages GPU resources. It will halt the GPU memory allocation when it detects its exceed of physical capacity and makes the program or process continue when other resources is deallocated. The current solution to solve this problem is tracking every GPU memory allocation, the allocation request. As shown in this picture, if the GPU memory allocation request will cause exceed of physical capacity, the scheduler will delay the allocation request of GPU workload 2 and continue it unless, and will not continue it unless GPU workload 1 finishes execution. However, the exact solution may cause the GPU memory allocation deadlock problem. GPU memory allocation deadlock problem means there are free space on GPU memory, but they cannot satisfy every task's request, and every task are waiting for the GPU memory allocation to continue their execution. So it means that every task will stop and not being continued forever. So we reproduce these issues by using the existing solution with 4 memory GPU tasks. The left figure shows after 230 seconds, all the tasks are stopped to waiting for GPU memory allocation, but none of them can establish the allocation. So we analyze the situation, and the figure in the right side shows the detail at that moment. We can see at that time, the free GPU memory size is 1.27 gigabytes. However, each task requires more than 1.27 gigabyte memory allocation to continue its execution, and thus none of them can continue their execution. So in this paper, we proposed the FlexGPU framework, which means multiple GPU workloads can use GPU flexibly without constraining OOM error as well as deadlock issues. The key point of this framework is using the host memory and transfer contents in GPU memory that are not being used to the host memory, and bring them back if they will be used again. In our design, we use a wrapping module and a scheduler to manage GPU memory allocation and deallocation. The wrapping module accepts CUDA memory allocation and kernel issue API calls and retrieves the necessary information and transfers them to the scheduler and let the scheduler make a decision. Here is the architecture. Each application is binding to a separated wrapping module. The wrapping module intercepts the GPU memory allocation and kernel launch API calls and retrieves the parameters such as application ID, allocation size, memory address, kernel arguments, etc., and makes the request wait in the waiting queue. And the scheduler will monitor the current execution status and decide whether the upcoming request should be executed, wait, or being checkpointed. So this slide shows the control flow of FlexGPU. First, the memory allocation and the kernel issues are grouped, and we call them grouped kernel. And the grouped kernel will be inserted into the wait queue. The wrapping module will send the size of the memory allocation request and the kernel's name to the scheduler, and the scheduler make a decision to send it back to each module. So the decision includes the issue, wait, and checkpoint, and the module will execute next step according to the reply. So in here, issue means the memory allocation will be executed immediately and the kernel will be executed immediately. Wait means wait for the future replies, and checkpoint means checkpoint some of its unused GPU contents to the host memory. So this is an example that how our proposed approach can solve GPU memory of subscription problem. So let me use the previous example. So suppose A1 and A2 are using the GPU memory at the same time. So GPU memory request of A2's second kernel cannot be satisfied. So we can see that from figure A. And since the memory contents of A2's first kernel is currently not used, so it will be checkpoint to the host memory. And after A1 and A3 finish, the scheduler will bring back A2's checkpoint contents and let A2 continue its execution. Then we will talk about the evaluation. Here is the evaluation setup. We use NVIDIA Titan XP with CUDA 99.0, and the NVIDIA Titan XP contains 3,840 cores with 12 gigabyte GDDR5X memory. And we also used Intel Xeon E5 CPU with 64 gigabyte DRAM. So the target workload from the Rodinia GPU benchmark suite and two real workload, which are memory GPU and the Blast GPU. So then we'll show the execution time of executing memory GPU in 4 different scenarios. The first one is sequential execution, which sequentially executes each instance one after another. And the second one is compact execution, which manually compacts multiple instances to make them run in parallel. However, because there's no additional mechanism to make sure all instances can fulfill their GPU memory allocation request, so several instances may suffer from OOM failure. And the third executing scenario is called allocation wait scenario, which delays CUDA memory allocation call to make them wait until there's enough free memory, which may cause deadlock that I've already introduced in previous slides. And it shows that due to the lack of necessary GPU memory management method, the memory GPU experienced OOM failure when the number of concurrent running instances exceeds 3. And in the compact scenario, meanwhile, due to the deadlock issue, the number of safely parallel running instances is also limited in the allocation wait scenario. So when compared to the sequentially running scenario, our proposed FlexGPU achieved a 7 times increase in speed of memory GPU. And by using our proposed FlexGPU, so the system can handle at least 8 instances of memory GPU running concurrently and safely. Then we demonstrate the average execution time of 6 applications from the Rodinia benchmarks. In particular, as DWT2D and LavaMD, since they requires more than 2 gigabytes of GPU memory, the number of concurrent running instances is limited to 3 and 5 respectively. The other 4 workloads can execute 8 instances concurrently because they basically require less GPU memory. So as a result, FlexGPU could enable safely running 8 instances of all the applications, even includes the DWT2D and the LavaMD. Here we show the overhead of FlexGPU, so we can observe that the client and server initialization are relatively costly, even if they are called just once. This is because in our approach, the wrapping module, which acts as a client, and the scheduler, which is referred as the server, must manage the necessary information that are stored in their individual memory spaces. And allocating memory spaces for this information requires a longer time. And it should be noted that both the cost of pre-launch and post-launch are less than 60 microseconds. Further, although these costs are counted every time when the corresponding CUDA APIs are called, the overhead is still acceptable when compared to the execution time of the application. And in the case of overall overhead, we compare the execution time for running one instance of memory GPU, GPU Blast, and relocate with and without FlexGPU. Here, we only focus on the CUDA scenario. So owing to the overhead mentioned in the previous section, the overall execution time of FlexGPU is generally longer than the original CUDA version. However, the overhead can be neglected as the largest difference is 110 microseconds when compared to the execution time of like 600 microseconds. From this evaluation, we can conclude that although the wrapping module and the computation overhead exist in FlexGPU, their impact or negative can be like not so important. Finally, we shows we shows how FlexGPU works in a real case. So the above figure shows the GPU memory usage when we running 3 memory GPU and 3 GPU blast together. So the above figure shows the GPU memory usage of GPU as the time changes. So it can be observed that after like 600 seconds after the launch, the total amount of GPU memory exceeds the physical capacity and causes failure of several instances with the OOM error. And this figure below shows the details of how FlexGPU handles this situation. It can be noticed that 835 seconds after the application is launched, the FlexGPU detects as the current launching kernel would cause the GPU memory to exceed the capacity. So consequently, it checkpoints certain unused contents to the host memory. And it shows, as a result, running 3 memory GPU and 3 GPU blast concurrently with FlexGPU. And when the checkpoint part becomes necessary again, then we can observe that FlexGPU brings them back to the GPU memory and continues the execution of the corresponding kernel. So in this paper, we proposed the FlexGPU, which allows the GPU memory contents to be checkpointed and restored to improve the availability of each application. Consequently, it ensures that more GPU applications can share the GPU simultaneously. The evaluation demonstrated that FlexGPU improves the performance up to 7 times and enables 2.6 times more applications to share the GPU. Thank you. And this is the end of